To answer the question above, let us first revise how orbitals are filled with electrons. Remember the off-Bohr principle? Take manganese, for example, with an atomic number of 25. We know that there are 18 core electrons, and we can use the noble gas symbol to represent that. We also know that the next orbital to be filled is the 4s, which can hold up to 2 electrons. So the remaining 5 electrons are filled in the 3d orbitals. Therefore, when filling electrons, the outer 4s orbitals is filled before the inner 3d orbitals. Both the 3d and 4s orbitals are valence orbitals. Therefore, electrons can be lost from both of these orbitals when forming cations. However, electrons are lost first from the orbital with the higher quantum number, that is, in this case, the 4s orbital. And then electrons will be lost from the 3d orbital. This applies to all first-row transition metals. Let us look at a couple of examples, the manganese 2+ and the manganese 4+ cations. In order to avoid errors, there is a systematic way of doing this. First, we write out the electronic configuration of the element in its ground state. To form the manganese 2+ cation, we need to lose 2 electrons from the element. And since we lose these 2 electrons from the 4s orbital first, we get the electronic configuration of manganese 2+ cation to be shown here. Similarly, to form the manganese 4+ cation, we need to lose 4 electrons from the element. First, we lose 2 electrons from the 4s orbital, and then the other 2 is lost from the 3d orbital. So we end up with the configuration shown here. For cations, it is also important to note the Dn configurations. Transition metals can exist in various oxidation states. Take, for example, chromium. The most common oxidation states of chromium are the +2 state and the +3 state. Each of these different cations needs to have its own distinct name. The convention for naming cations is as follows. First, we write the name of the element, followed by the oxidation state of the cation in brackets. The oxidation state is written in Roman numerals. So the name of the chromium 3+ cation is written as shown here. Likewise, the name of the chromium 2+ cation is written as shown here. So we have two distinct names for these two ions. It is also acceptable to use the chemical symbol instead of writing out the word chromium. So alternatively, the names can be written as shown here. The method that you have just seen for naming cations is the most modern way of naming them. There is, however, an older method. The older method is still sometimes used nowadays, and you may still encounter it in some textbooks. You may notice that chromium 3+ ion has a higher charge than the chromium 2+ ion. In the old method, they use an "ic" ending for the ion with a higher charge and an "os" ending for the ion with the lower charge. One easy way to remember this format is that there is an "I" in the word higher and there is an "O" in the word lower. So the chromium 3+ cation was called the chromic ion, and the chromium 2+ cation was called the chromous cation. Now let us look at how a transition element is defined. The International Union of Pure and Applied Chemistry defines it as an element whose atom has an incomplete d subshell, or which can give rise to cations with an incomplete d subshell. Notice that the definition has two parts separated by the word "or." This means that if an element meets either one of these criteria, it can be classified as a transition element. So if we look at the electronic configurations of the first row transition elements, we can see that it is obvious that the elements from scandium to nickel all have incomplete d subshells. Hence, they qualify as transition metals. If we look at copper and zinc, we see that they both have filled d subshells. However, copper has the ability to form the copper 2+ cation, which has a D9 configuration. So copper qualifies as a transition element. Now when zinc forms the zinc 2+ cation, it loses those 2 electrons from the 4s orbital. So the zinc 2+ cation would still have a D10 configuration. So zinc is not a transition element according to the definition above.